morning, guys. Let's talk a little bit about work today and energy and get into a few problems here and some notes. So step out of the way. These are your notes. If you watched the video 603, this is the first part of 603. So we'll go into the second part later on. I'll step out of the way so you can copy your notes down. All right, so first thing, let's talk about energy. Okay, we haven't talked about energy yet. We're going to get into it a little bit later after this. But energy is just the ability to do work. We're going to leave it at that for right now. Work. What is work? Okay, when I do work on an object, I have to exert a force. And when I exert that force, something has to move, okay, because of that force. We're going to get into some different scenarios with that in just a minute. So, got your basic definition of work there. Work is a force times a distance. Not a hard equation right here, right? We're just multiplying. So work is a force times a distance. As far as our units goes, the unit for a force is a Newton. The unit for a distance is a meter. So we have a Newton times a meter is going to be our unit for work. All right. So let's talk about some examples of that. What does doing work mean? I'm going to do some work on this pen, right? I'm going to lift this pen up into the air. So which way am I applying that force? I'm applying a force in the upward direction. And what direction is that pen moving? The pen is also moving in that direction, right? So I am doing work on this pen. In other words, I'm giving energy to this pen. If I lift it up, I'm giving it what we call potential energy. And we're going to talk about potential and kinetic energy in just a little bit. But when I lift it up, I'm giving it energy, okay? When it is falling down, what's doing the work then? That's right, the earth. The earth is doing the work then, right? Because the earth is applying a force. Now think about which way the earth is applying a force. It's applying a force downward. In which direction is it moving? It's moving downward. So the work being done on a falling object is done by the earth. The work being done on a lifted object is done by some other object, me in this case, right? Now, what about moving sideways? If you're pushing something sideways across the floor, well, you would be pushing it with a force in this direction, and it would be moving in this direction. So, the unit for a force is a Newton times a meter, but that also equals this new unit we're going to talk about, which is called a joule. A joule is the unit for work, and it is also going to be the unit for energy. We're going to talk about joules of energy here a little bit. So, now we've got some examples you're going to need to know about. So as long, let me erase my board here. Now, if I was picking up a box, we would be applying a force in this direction, right? And the box would move in this direction. We would be doing work to this box. What if I was carrying the box? What if I was holding the box right here in front of me and walking to the side? I can't move very much here, I'm sorry. But if I was walking to the side, am I doing work on that box then? Well, let's look at our arrows. What would happen to our arrows then? If I was carrying the box, which way is the box moving? The box is moving this way some distance, right? If I'm just carrying the box, which way am I applying that force? I'm applying that force upward on the box. Now this is one of those times where it may seem a little confusing because in this case, I am not actually doing work on the box. I fill the box, it's heavy, I'm moving the box. Why am I not doing work on it? Well, it is because the force and the distance are now not in the same direction. Notice they are perpendicular to one another. You can only be doing work in the physics sense if your force and your direction is in the same plane, so to speak, right? Or in the same direction. So keep that in mind as you go over any examples. Make sure your force and your direction of movement are also pointed in the same direction. Therefore, you are doing work on that object. All right, so I'm going to look at our first example problem. You can look along the notes with me. I'm not going to write the whole problem up because I don't have room on my board here. I'm just going to write the numbers, but read the problem. Okay? So what work is done when a refrigerator is pushed uniformly 12 meters across the floor, the force of friction between the floor and the refrigerator is 480 newtons. So let's start by drawing our problem. I'm going to draw a dot for my refrigerator. I'm going to start labeling my forces like we always do. Okay? The force of friction between the floor and the refrigerator is 480 newtons. So that means if I'm pushing 480 newtons this way, okay, that means there's 480 newtons of friction I have to overcome if I'm pushing this thing uniformly. Remember what uniformly means? All the forces are balanced. Now, the distance I push it for, it gave me in the problem, it said was 12 meters. All right. So how much work did I do? So work is force times distance. I'm going to plug in my force of 480 newtons. I'm going to multiply it by my distance of 12 meters. 480 times 12 is 5,800 joules of work, or Newton meters of work. Either one would be correct. Okay? It's not bad, right? Pretty simple. Plug it in, get a number. Let's do another one. Okay, what work is done when a 200 or 2.5 kilogram package is lifted 2.2 meters? All right, I got a 2.2 kilogram package, or 2.5 kilogram package, and it's lifted 2.2 meters. Well, here's a trick, and some of you probably have already spotted this. How much force am I lifting up with? Well, 2.5 kilograms is not a force, right? That's a mass. So let's make that a force. 9.8 is kind of confusing, so let's just multiply by 10, just to know. So we got 2.5 times 10 is going to be 25 newtons of force upwards, right? 25 newtons of force upwards. So work is 25 newtons of force, and we're moving upwards 2.2 meters. All right, and that gives me about 54 or 55 joules of work, depending on whether you use 9.8 or 10. So I think my answer had 54, but I used 9.8 in my example problem here. All right. Now you have a few more example problems there. Now there's one more case where it gets a little bit different. The only other way to spice this thing up, so to speak, is if we were doing work at an angle. What if we were pulling a sled? When you pull a sled or pull your little brother, you don't pull in a straight line. Usually you pull at some angle, right? Well, now we have this thing theta. This should look kind of familiar to you. So remember, if we were pulling our sled, let's just say we were pulling at 23 degrees. Let's say we were pulling our little brother at 23 degrees above the horizontal with a force of 47 newtons. How much force is now doing, or how many joules of work are now being able to do it? Oh yeah, we gotta have a distance here. We're gonna pull our sled 5 meters. So how would we do that? Well, we gotta remember that only the force being used in the direction is going to be doing the work. We have this force 47 newtons, but some of that force is being used to pull horizontally, and some of that force is being used to pull vertically. Well, pulling up on the sled doesn't make it go anywhere. What does it do to the horizontal force? Oh, it's going to make our horizontal force a little bit less than this number. Remember, h times the cosine of theta? That's how we figure out the length of this side, right? So this is going to be 47 times the cosine of 23 degrees. That's going to take care of this side of the angle of this side, and we're going to multiply that by 5 meters. Okay, so all you got to do, now you got to put it in your calculator. You got to remember, now you got to do this part backwards. 23 cosine button times 47. You can go ahead and equals and get all that equals, and then multiply that by 5. And once we do that, we should get 216 joules of work to do that. All right. Now you should have a worksheet work that goes with this. I think it's 613 is the number, so I want you to go ahead and look on that. If you need some questions with the blanks, you probably still want to go back. If you can't fill them in from my notes here, you need to go back and watch 603 because 603's got everything. I'm just doing these notes to kind of fill in gaps and just to communicate with you. But you still need to go back and watch the regular videos to get all of the notes and all of the example problems in there. Okay? I'm going to leave it at that today, and I'll see you on the next time.